Hello, everyone. My name is Konrad, and I'm a gameplay programmer at Full Theory. You may know us or not know us. We created games like The Thaumaturge or Seven. Now we are working on The Witcher remake under artistic supervision of CD Projekt Red. And in that company, I'm working using stuff that I want to show you today. For example, so this is one of the approaches that we can do when we created gameplay features. So this is a quick look at the agenda. Firstly, I will show you how CPU processes data, because this is kind of important to understand why we are even want to think about moving from object-oriented approach to data-driven approach. So I want to everything was clear for everyone, because maybe not everyone know how it looks like. Later, I will show you some examples, how we can use that data-driven development in games, and at the end, there will be some time to talk about that, I think. Okay, so first, how CPU processes data. So if you ever program stuff in any language, I think, but I will be using C++ here as an example, you know more or less how it's working. So if you, for example, create some struct, and this struct will have some variables, these variables will have some space that they need to take some space from your memory. Yeah. So depends on the type you use. This may be 1 byte, this may be 4 bytes. So everything depends. And when we are trying to allocate that space in RAM, they are like the CPU trying to find a place for that. They trying to find where there is enough space to allocate that, and is placing that in our RAM. And this must be placed in a good position. So each depends on the size of our data. Different pointers will be used, because pointer address must be divided by the size of the data we want to allocate. So sometimes there will be some, when we are trying to create object, from example from that struct, there may be some blank spaces between data. So you can see this is that yellow rectangle. There is 3 white rectangles, which is like blank space, and this is some blue. So this is what we are called memory alignment. So each data must be stored in a memory that must begin at the address that is divisible by the size of the data. So that's where this is that blank space. But this is not work like that we have some like missing memory here, because our CPU are I'm placing here some dummy data to have one continuous struct of data in that memory. We are not really be talking about that much, but I want you to know that this is some space that is filled between these variables. So it's not like this is like empty space. And now, when you want to do something with that struct, so you have that struct, you have struct that has 2 variables, and you are saying, okay, I want to perform some operation using that timer variable, for example. So you are saying that the CPU, and CPU has something what is called cache. And these caches are 3. There are 3 of them. They have different purpose, and they have different speed, I would say. But each of that cache is much faster than getting data like directly from the memory. So when you are saying, for example, I want to perform operation using the timer variable, CPU will check if has that data loaded in his cache, for example. So he will like to say, okay, if do I have this data here in L1 cache? If not, it will check in L2. If not there, it will check in L3. And if not, like there is no data in any of that cache, it will have to load that data to cache using your random access memory. Yeah, so here will be something we call cache miss. And why this is important? Because for CPU, like on your architecture of your hardware, when some data is loaded to cache, this is really, really fast for CPU to get that data. So if something is in cache, it will take you nanoseconds, milliseconds to get there. And if you need to go to your memory, it will be much slower. It's not like super slow, but in some cases that might be visible if you have a lot of objects, which we will talk about that later more. Okay, so this is what is called cache miss. And if you want to have super fast code, your target, your goal should be to not have a lot of cache misses. Okay, but we have cache miss. So what will happen next for CPU? CPU will say, okay, this is address I want in my cache to do some operation on that. So we are not loading only this one part of data we have here, because depending on the processor, data is written in blocks. So we are not loading only one variable, for example, to the cache. We are load the whole chunk of the memory. And this might be 32, 64 bytes most often, but depends on CPU. We will use in that example the 64 bytes. So when you are loading data to CPU cache, we are loading the whole chunk. So we are starting from boundary of that data. So if this is, for example, 64 bytes chunk, we will start, for example, from 0 to 63 address, later 64 to 127, and so we are jumping addresses by 64 if we are using CPU that load 64 bytes of memory. So even though we want that address on on 44, for example, that pointer with address 44, we will start with address 40 and we will load the whole chunk. So the CPU will load starting from there, load the whole 64 bytes of memory. Yeah. So this is how CPU works, and what is doing here, he's loading that, and we are calling that cache line. So when the CPU is loading something from RAM, it's doing that using that cache lines. And each cache line might be that 63 bytes, 64 byte, or something like that. And when this is loaded to the cache, the whole chunk is loaded. So we are loading additional data with that chunk. So even though we wanted only that one variable, for example, timer, we also loaded that ID variable, the whole struct, and all the data that was next to that struct in our memory. And thanks to that, if you, for example, want to do something different, for example, we want to do something with ID, so not with timer variable, but with ID variable. So we are using different variable, but now when CPU will check in that L1 cache, this data will be there, because together with that timer, in that whole chunk, there was also ID variable. So thanks to that, CPU will get the data from there really quickly, and that will be super performant for your gameplay or for your code. So conclusion is that from that introduction, that CPU will process data that is contained in one continuous block memory the fastest. So you won't have data next to each other to have the most performant way to process data that you can. And keep that in mind, because now we are going into object-oriented programming, and we want to see how this approach to programming, that is most common one, I think, how this is utilized, how that memory is stored by that paradigm, by that approach. So I have some sample code there. This is really, really simple code. We have one class, one actor in Unreal Engine. And here we have mesh component, which will render some object. We have time accumulator, and we have tick to do some stuff. And what that code will do is just scaling up cube up and down. So this is like pulsing cube on your scene. And what I'm doing next, I'm just spawning a lot of these cubes on grid on my scene. So when you're doing that, so you are spawning the cube on your scene, your memory might look like that. Of course, this is simplified image of that. So these lines here, so they might be much farther away from each other. So it's not like that this yellow is here and two lines below that this is another memory that maybe in normal situation they will be much farther away from each other, but it's easier to show you that way. So when you create, for example, that cube, and you are allocating that object will be allocated in one place of the memory. And together with that object, you allocate some pointers, which will point to other part of the memory. And in that other part of the memory you will allocate the concrete components you want to use. So for example, that yellow color here, here's your object, and this object has pointer to static mesh component. But that static mesh component is not allocated together with that object. It is allocated in totally different place in your memory. So if you want to do something with that static mesh component, you need to dereference pointer, go to totally different place in your memory, get that object, and thanks to that, you can do something with it. So here, like you can imagine, you cannot use cache lining. I would say CPU cache will not be used in performant way, because in one cache line you have one component, and if you want to use something different, it will be in the totally different place of the memory. So you need to load that data again to CPU. So this will be difficult to reuse. Okay, so this is one object. But if you allocate second object, these components and this float timer accumulator, it won't be next to each other. It will be in the different part of memory. So the object will be next to previous object if you are allocating one after another, like I was. But only that object will be one after another. But the mesh component and time accumulator might be in the totally different part of the memory. Depends on what happened between of that. Yeah. So because of that, still, when you iterate over that object, it will be not really performant to do some operation on that. Okay, so now I created here that, like I said before, I created some scale changing cube, and I want to iterate over all the cubes I have on a scene and just like change its scale up and down. So this is like simple code, nothing really fancy. And this is looking something like that. Yeah. So what we wanna do there, we wanna present what will happen if I want to execute one function over big chunk of objects. So a lot of objects and one operation, and I'm iterating over it like every frame, and I want to do that something with that. And in that object-oriented stuff, because of nature, how that memory is stored, you need to go object by object, because each object has its own memory layout. Each object has its own pointers, and these pointers are pointing to some other part in your memory. And if you want to do something, you need to go to one object, you need to go to the reference that pointer, go to the data in memory where that pointer points, load that data. If you want to next object, you need to go to next object, the referencing another chunk of memory, load that to load that to CPU, next object, next chunk of memory, next loading to CPU, because these pointers are like not next to each other, they are farther away. So this is not like on our first example at the beginning, that when I created second, when I loaded that one variable in, like I loaded two variables because they were in one cache line. Here you are not doing that, because when you load one cache line and you want to create something on different object, that different object data won't be in that cache line. So you need to load another cache line, and another cache line, and another cache line. So you need to jump on the memory from place to place. And of course, this will be quite fast if you don't have a lot of objects, but when your object going up, this will be difficult to maintain. So if you look on for example, profiling stuff, you can see that operation is there's a lot of execution. Yeah. So if I have, for example, 100 objects, I need to create 100 executions. So it's really difficult to execute the same operation on the different objects. I need to process them one by one. And because of that, I need to jump on memory one by one. So this is difficult to optimize in that object-oriented approach. So when we look at the numbers, of course, because you may say, okay, but when I should be scary of that, yeah? So this depends what you are doing, because of course it's not like object-oriented programming is bad. It's of course good, yes, but you need to answer question. Okay, if my system, my game, if I have enough resources to do what I want to do. So if I want to, for example, do that stuff on 100 actors, it's not a big deal because it's only less than millisecond. But when your number of actors is growing up, the time is also growing up, and at some point you don't have enough milliseconds in one frame to execute that operation. And what I'm doing here is really simple operation because I'm only doing like scaling up, scaling down. Yeah. So in normal game, this is much more complex, and you have much less time to do something like that. So when your actors number growing, your time is really valuable, and you need to think how to fix that. Okay. So what problems are with object-oriented programming when we are trying to do something like that? So data are scattered throughout memory. So we have frequent cache miss because CPU must jump from place to place and load the different chunks of memory. So they are not next to each other. They're not connected. So we are not utilizing what CPU is good at. So loading a lot of data in cache and later loading that from cache because there are no cache for that. We are chasing pointers. So the engine needs to access nested objects, which requires a lot of pointed referencing because this is how objects are created. Yeah, so we have a lot of pointers. They are pointing on different places in memory, so we need to jump from place to place, like I said in before. Tick overhead. So it's more like engine thing that we have a lot of many virtual calls because inheritance and this is how object-oriented stuff is working. And also we have some memory bloat because when we are creating some new object or actor and stuff like that in Unreal, we are not creating only stuff you want to use. So even if your actor, for example, has 2 variables you want to use, it will be allocated much more memory that is useful by engine to work. Yeah, so you have some variables for naming, variables for stuff that to display stuff in the engine and so forth and so forth. So there's memory bloat. So you need to allocate much more memory than you use. So if, for example, you use one variable which have 2 kilobytes of size, but your whole object will have 7 kilobytes, for example. So I would like just shooting with numbers, but it's work something like that. Okay, so how we can approach that differently? So to approach that differently, we need to start to think in other way about processing the data we want to use. So that's when data-driven development is coming into action. And data-driven development in Unreal Engine is we are doing that using MAS. It's like plugin provided by Epic Games. If you are using Unity, for example, you maybe heard about ECS, Entity Component System. This is pretty much the same stuff. So in both engine, like the approach for that is same, I would say. But of course, like naming may be kind of different because of naming convention used by developers. Yeah. Okay, so what we want to do, we have data scattered throughout memory, so we want to related data to be kept in a single memory block. So thanks to that, CPU will load with one cache line a lot of data and later use CPU to load that. And thanks to that, it will be much quicker. We don't want to have a lot of pointers everywhere. We want to access memory block directly. So without pointer dereferencing, we want to iterate over memory. We want to change. So then, thanks to that, we eliminate the referencing problem, and this will be much quicker for CPU to do. With tick, because each object has its own tick, so we need to like you said, like you saw in my profiler, a tick is executed one by one, so object by object. So we don't want to do that. The best would be to iterate only over the data we want to change without need to call function per object. So to execute that in one one function, for example. So that would be nice because we will have only one call instead of 100 calls, for example. And we only allocate data we use. That's goal we want to achieve by moving into data-driven approach. So how we can store our data differently. So in Unreal Engine, like I said, there's that mass plugin, which provides something like that. And this pretty much looks more like that. So we will go like step by step what all of this is. So what is fragment, what is archetype, what is entity. But in like general, instead of treating everything like an object, we want to store our data in the arrays and iterating over that arrays. So how this will work? So let's start with fragment. Fragment represent data used in calculation. So fragments include transform, velocity, LOD index, etc., etc. So you can treat them like some collection of variables you want to use in your object. Yeah. So, for example, when you have fragment transform, that could be, for example, position, scale, and rotation, for example. That will be transform fragment. And this is only to store data. So there is no logic there. This is only storing data, nothing more, nothing less. Next stuff, we have entity. An entity is a collection of fragments that make up a specific agent or actor. So each entity has an assigned ID, which tell us which fragment belongs to whom. So, for example, when you create 5 actors or 5 agents on your scene, and each of these actor will have transform fragment, for example, these fragments will be stored in one array, which will have 5 records in it, and each of that entities will have ID. Yeah, and using that ID, you can get from that array data which belongs to the specific entity, specific actor. So when you are iterating over that array, you are using that entity you want to edit using its ID. So this is just ID. So entity is just ID to use the data from an array. So fragment entities only define the data we operate on. There is no logic there. So this is important to have it in mind. Next stuff is archetype. So archetype is a collection of entities with identical fragment composition. So each archetype is unique and is constructed from different fragments. So you can, if you want to think about that like you would think in object-oriented programming, your archetype is kind of like class, I would say. So because in that archetype, you are like just like saying, okay, for that to achieve some feature, for example, I want to use this fragments and these fragments. So I want this. I want these variables and these variables because I need to store data from calculation in these variables. Yeah. So this is kind of like some composition of fragments that will be used to spawn some actor on scene. Okay, and how to process? Because what we say now is like to like we want to define some like we want to define some some data we are operate on, but how we operate on that data, that's maybe a question. So to do that, we are using something what is called processor. So processor is a single class that is responsible for executing logic and updating state of the fragments. So here in that approach, you have to tell like your data is in one place and your logic is in other place. So they are not connected. So like in the class, you have fields, you have functions in one place, but there will be totally separated. Yeah, and processor is something what we say this is our function. Entity query is something we are using to get actors we want to change. Yeah, because you have entities that those entities have a lot of different fragments, and maybe you want only actors that have this fragment and this fragment. So with that query, you can filter it out and only iterate over that you want to really change. And the last thing, which is important, is trait. Trait is like a collection of fragments that must create for a given entity to provide specific functionality. It's used mostly for organizing stuff, yeah, because you want to, for example, if you want look at a feature, for example, you want some fragments to be always there to provide that feature. So you don't want to do that to keep it in mind which fragments I need to provide look at target. You want to like group them in some trait, and later if you add some trait, all that fragments will be added automatically, and you don't need to think about that. Yeah, so there's some kind of organizing stuff. So okay, so if you look at object-oriented programming, you will see that you have hierarchy of classes, a lot of inheritance, everything is connected, and data and logic are packed together inside the class. Each object stores its own memory layout. Components are nested using pointers and scattered across different memory locations, and it's difficult to process the same data from different objects in groups. In mass, on the other hand, you have arrays, and arrays store your data. So its data and logic are completely separated. Data is stored in fragments, and entity contains only an ID. It stores no data. Fragments are grouped in memory by archetype and held together, and data is processed per archetype for all entities that match it. Okay, so if you want to move from that object-oriented approach to data-driven approach, we can use our class. And in that case, that mesh component we are used maybe some rendering trait, so some fragments provided by plugin or something we want to create that will render that stuff. So this is one thing. That timer accumulator might be some fragment we want to use, and processor instead of tick to provide that scaling up, scaling down feature. So we create fragment with that accumulator. Next, we create a trait because, of course, scaling up, scaling down needs some fragments. So we need transform fragment to have that position, rotation, scale, and we need that timer fragment to create that animation. Later, we can like set that up in the unit in Unreal, and we have some data asset for that. So we are setting, okay, we need the trait for mesh visualization, we need that scaling trait we created. So like we are creating here archetype. Yeah. So we are saying, okay, we need these fragments when actor is spawned to process it later. And that's how it looks in the editor. So you just saying like you have a special object that you can place on the scene. You are attaching that entity config, and here this is your archetype, and you have that on your level. So that's how it looks in object-oriented programming. Yeah. So data are in different places in memory, and in data-driven development, this is how it looks. So transform and timer are pretty close to each other, and if you create another object, that data still will be next to each other, and so on and so on. And so this will look like that. Yeah. So entity one will be this part of the memory, entity two will be this part of the memory, and thanks to that, if your CPU is loading it, you will have it in your cache pretty quickly, and it will access it pretty quickly because it loads a lot of the data by one cache line and don't need to jump from place to place. Okay, so at the end we have that processor. So how we want to do that? So in that processor we need to do two things. First thing, we need to create that query I said. So we are like saying, okay, to this processor to execute, it needs all the entities that have transform and timer fragment. And from all the entities in the memory, we are like filtering out only this with these two fragments. So if they are here, we are using it. And later we are just getting to that chunk of the memory. We are iterating over entities, and our iterator, so our index is the entity ID. And we are getting the view on that array with that fragments, and we are just like getting that fragment from that array using index, and we are doing stuff on that. and we are like passing this to that array. So we are not using pointers, we are like iterating over the memory directly. So this is super fast. And thanks to that, we are doing this in one go. So this is only one call. Instead of 100 calls like in object-oriented programming, we have only one call, which is much quicker because we are utilizing that CPU caching lines, and this is super quick. So if you look at some numbers here, you can see that with this approach, even if you have 10,000 of actors, this is still less than 1 millisecond. And at some point, object-oriented programming is not even usable. And with mass, you still have some time, which is, so this is really difficult to make it to be not performant, I would say. So this is really cool to have it next to each other. Yeah? And when in your game you can use that, because my example was super simple. So you can, for example, use it to crowd simulation. When you have a lot of NPCs in your game, this could be it. When this is a lot of objects, and it's easier to treat them as a group, not as a unique object. You can use it in bullet hell, where there's a lot of bullets, I would say, floating everywhere on the scene. So this will be much more performant using it that way. You can use to environment effects, for example, because there's also a lot of objects that need to be handled in large-scale systems, like in grand strategies. There's also a place for mass system. So, summary, last thing. So it's not like that OOP object-oriented programming is not usable. It is usable, but you need to decide where to use it. So if you need the complex unique behavior and you rely on built-in systems such as physics, collision, animations, you design mechanics that are heavily oriented on working with editor tools, blueprint, level design, the number of objects is limited, and you care about its debugging, object-oriented programming is super cool for that. So if uniqueness of object is important for you, object-oriented programming is super cool. But if that uniqueness is not that important for you, but you want to treat some group of actors as a group, so you can iterate over it and do some stuff, then mass is super cool for that, because you can handle hundreds of thousands of actors pretty quickly. Objects share simple data and behavior. You care about maximum efficiency. You want centralized data-related logic. So bullet system, crowd system, status effect, particles, environment effect, all of that is super cool when you use mass, because you can do it in one go. You can utilize CPU cache, and this is super quick. So I would say OOP for uniqueness, and mass for something that should be treated as a group, but by your code. And that's everything from me. So thank you for your attention, and I hope you're still with me with that technical stuff.
Hello there. It was a red presentation, but alongside that, we've unfortunately lost Matt. He has some pretty heated argument with his internet provider. So yeah, we had some obstacles. So while he was still with us, he had a question, specifically as a mostly C# developer, what actually mass means, the acronym.
Oh yeah. That's very difficult, because I checked that. I will check that, because I checked that yesterday, because I thought it will be a question like that.
So while you are on the search, Ryder at the JetBrains can actually show the alignment in tooltips for your fields of the object. Although recently, while we were digging heavily into different compiler implementation, turns out that every single compiler toolchain like GCC, Clang, and MSVC, they use different semantics and differently align the structs depending on the attributes that you use for the structs. So be aware.
Yeah, that's true.
So yeah, sorry, I've been having kind of technical difficulties back here, so I missed a couple of things with the mass. Is mass a system using yourself created, or is this something that's available for others to use?
Yeah. This is usable for everyone because this is how Epic wanted to have, because they wanted to have some plugin that utilized that data-driven approach in games. So they provided that mass plugin like some time ago, but it was experimental for some time, and now like I think some versions ago it become like part of the engine that everyone can use, and you can like do stuff with it. So it's not like super it's not like unique stuff that I created. I'm sharing with you. It's like mass is Unreal part, so you can use it. And I only wanted to show how it could be useful for you.
Yeah, no, that's cool. I hadn't realized it was by Epic and it was actually part of the engine now. So that's really useful. It's going to be available for everyone to use.
Yep.
So ChatGPT says that mass is actually like a massive array of structural simplicity. So maybe just like a
might be. To be honest, I never think about that, because for me, like I heard word mass. For me, it would be it's obvious because there's a lot mass of factors I want to handle. So so for me, I even like didn't thought about that it will be what is underneath. Yeah.
For me, it just sounds like a fancy way to say like the instead of the array of structs, the struct of arrays.
Yeah. That might be that, because on the when you see look at this, okay, this is a struct of arrays, but underneath you need to like switch your mindset, I would say, how you organize data to have that struct of arrays at the end. So I think if you say struct of arrays, it would be the whole picture. So that would be like misleading for someone. Yeah.
Mm-hmm. Mm-hmm. It does feel like a very different way of thinking about your data and everything. How easy is it to rewrite from one system to the other, from classic object-oriented to something like mass?
Okay, so that depends mostly on the system, because of course, if system is quite simple, it will be quick. But with this is really big system, it will be difficult. But take months, hours, months, years, even. So I think it's not the best idea to go with totally revolution of your system. It's better to, for example, if you have huge system in right in object oriented, you should use your profiler, find places that are not really performant. So when you need to optimize it, and just move only that places. So these critical places that are most heavy, that should be moved, and that could be like that. So some kind of evolution, because it's not like you can easily move object-oriented into data-driven, because you need to rewrite how data are organized, because this is a totally different approach, totally different mindset, everything is different. So it's easier to find what should be moved and move that step by step. And it's difficult to say how long could it be, because it's case by case, and you need to find places you want to move. So I would recommend something like that.
Mm-hmm. Would you go straight to something like mass, or would you do object-oriented first and then only change when you've measured and you can see that actually you need something a bit more performance?
Well, I think still my favorite saying depends on the system. Yeah. Because sometimes you have some system that you know from the very beginning that will be big, will be difficult to maintain in object-oriented programming, and in that case you can go straight to mass and don't care about object-oriented programming. But in most cases, I think you can start with object-oriented programming. So, for example, in that example I said about bullet hells, for example, you can start with object-oriented because this is easier for everyone, and maybe you wouldn't have that many objects to consider that a problem at any point. So in that case, you can stay with object-oriented because it will be easier for you to think, because it's easier. But if at any point you will see, okay, this is going to out of hand, my time is reduced, I doesn't have resources in my time frame, so in that case you should move. Yeah, so depends what you want to get. So if you know from the very beginning, okay, I want to use thousands of actors, you go mass, because with OP will be difficult. But if you have some number, but you don't really know at the moment when you will end up with that, you can start with object-oriented and you decide it later if you want to switch, for example.
It is nice to know there's a migration path, but also it's a classic software answer of it depends.
Yeah, it depends, because it always depends, unfortunately. Yeah. There's no easy answer.
It's always the best answer. Well, thank you very much for that presentation. That was really interesting there. It's a great visualization as well of how to understand this problem and how it can impact you as well. So thank you very much for that.
Thank you.
And Alex, have you got anything you want to add?
Nope, I guess not.
Very good. Well, then, thank you very much, Konrad. We'll say goodbye for now. Very much appreciate your time.